And now let's continue with the discussion. So, what is coefficient performance? COP is a metric that captures how efficiently a thermodynamic machine, for example, air conditioner, heat pump, refrigerator, and etc. These uses electricity to move heat from one place to another. Specifically, the COP is the ratio of energy needed for a system to operate compared to the system's useful energy output for heating or cooling. So a higher COP means that less energy is required for the same output. The COP is commonly used to evaluate the efficiency of air conditioning systems, heat pumps, and refrigerators. So we have here the formula and how to calculate the COP of a heat pump. So it's COP equals Q divide E, wherein the Q is the heat supplied from the heating or removed cooling by the system. E is the energy needed to operate the system, and the calculation differs depending on whether the system in question heats or cools. This is because opposite ends of the process must be considered. In a residential setup, the heat move out of cooling or move into heating. The building is considered. In a heating scenario, the building is the heat sink, which is the part of the cycle to which heat is added. In a cooling scenario, on the other hand, the building is the heat surface, heat is removed from it. So in cooling scenarios, the COP is calculated by determining how much heat was removed from the heat source. Therefore, the ratio of heat removed to input energy, for example electricity, to operate the heat pump is considered. And the COP cooling, which is this is the formula, equals QC divide E, wherein the QC is the heat removed from the heat source, E is the input energy. In heating scenarios, one looks how much heat is moved to the heat sink. This consists of heat taken from the heat source as well as the energy input. Therefore, the combined value of heat taken plus the energy input over energy input is considered. So here's the formula. COP heating is equals to QH divide E equals Q plus E divide E is equals COP cooling plus 1, wherein the QH is the heat added to the sink, the E is the same, it's the energy input. Okay, so to sum up, the heat moved to the heat sink is greater than the heat taken from the heat source. So therefore, a heat pump COP depends on whether the system is used for cooling or heating. And the heating COP is greater by 1 than the cooling CPO. We will now proceed with the discussion of thermodynamic cycles. So, what is thermodynamic cycle? It is a series of thermodynamic action that, when carried out repeatedly, leave the system in the same state as when it was first created. Thermodynamic cycles are used to explain how heat engines, which convert heat into work, operate. The thermodynamic cycle is a closed cycle that has many changes. This is due to temperature, pressure, and volume, but whose end and initial states are equal. So there are various types of cycles in thermodynamics, and some of those important cycles are the Carnot cycle, Rankine cycle, Otto cycle, Diesel cycle, Brayton cycle, and Stirling cycle. First, we have here the Carnot cycle, which is the French physicist Sadi Carnot proposed the Imogen Carnot cycle in 1824. It is the thermodynamic cycle. This is transforming heat into work or work into heat. This is the most effective cycle that is currently known to exist. The Carnot cycle consists of four processes that can be reversed. First is isothermal expansion, when a working substance, usually a gas, comes into thermal contact with a heated reservoir. It expands and takes heat from the reservoir with it. Secondly, we have adiabatic expansion. The functioning substance is thermally detached and extends, taking care of business with its environmental elements. We have also here isothermal compression. The functioning substance is in warm contact with the chilly supply and packs, emitting intensity to the repository. Lastly, we have adiabatic compression. The function substance is thermally secluded and packed, taking care of business based on its environmental factors. The Carnot cycle can be addressed on a temperature entropy graph as a closed cycle. The proficiency of the Carnot cycle is determined by the situation n equals 1 minus th divide Tc, wherein we can see here that Tc is the temperature of the cool supply and the Th is the temperature of the hot repository. Next, we have Rankine cycle, which is a steam turbine's method of converting heat into mechanical work is described by the Rankine cycle, a thermodynamic cycle, and the cycle is named after Scottish engineer William John McKern Rankine, who created it in the middle of the 19th century. And the Rankine cycle has four steps. Step 1, isentropic compression. Within a pump, the working fluid, or which is the water, is compressed from low pressure to high pressure, since no heat is added to or lost from the fluid during this isotropic process. So the second process, or the step 2, is heat addition, which the heat compressed water is next converted to steam by vaporization in a boiler, a combustion process such as burning coal or natural gas is usually used to generate heat. Step 3 is isentropic expansion. A turbine expands the steam, turning its thermal energy into a mechanical work. Additionally, since no heat is added to or taken from the fluid, this process is isentropic. So the last step is condensation. After that, a condenser converts the steam back into water. In this process, heat is released and often transmitted to a cooling medium like water or air. Next, we have Otto cycle. Nicholas Auguste Otto, who patented the first four-stroke internal combustion engine in 1876, is the inspiration for the Otto cycle. Many modern internal combustion engines still use the Otto cycle. However, each cycle, such as the Atkinson cycle, are still used in some applications. The Otto cycle is a simplified thermodynamic cycle that depicts how a common spark ignition or the piston engines work. It is the highest frequent thermodynamic cycle seen in car engines. The Otto cycle is made up of four processes. So here's the four processes of Otto cycle. First, isentropic compression. In the cylinder, the piston compresses the air-fuel mixture. Because this is an isentropic process, no heat is transmitted to or from the system. Next is constant volume heat addition. The air-fuel mixture is ignited by a spark, causing it to combust and expand. Because the expansion occurs at a steady rate, No work is done during the process. Third, isentropic expansion. The expanding gases force the piston down, causing it to accomplish work on the environment. This is an additional isentropic process. And lastly, we have constant volume heat rejection. The cylinder's exhaust gases are evacuated and the piston returns to stop of the cylinder. Because this is the constant volume process, no work is done during this time. Next, we have your diesel cycle. So the operation of a diesel engine is described by the diesel cycle, a thermodynamic cycle. It has a four-stroke cycle, which means that one cycle of operation requires piston in the engine to make four strokes. So here's the four-stroke. First is intake stroke. A vacuum is created as the piston descends in the cylinder, drawing in air. Second is compression stroke, which is the air is compressed as the piston rises in the cylinder. Since a diesel engine normally has a higher compression ratio than a petrol engine, the air in the cylinder is compressed to a significantly higher pressure. Next is combustion stroke. Injection of fuel into the cylinder occurs at the conclusion of compression stroke. Fuel is ignited by the heat from the compressed air, which causes it to burn quickly. The piston is pushed downward by the expanding gases, producing power. Next is exhaust stroke. Pushing the engine's exhaust gases outside the piston rises within the cylinder. The next cycle is Brayton's cycle, one type of heat engine that uses air or another gas as its working fluid operates according to a thermodynamic cycle called the Brayton cycle. Modern gas turbine engines and air-breathing jet engines also follow the Brayton cycle. However, the original Brayton engine had a piston compressor